Right, so thank you for coming to Bath Astronomers for our January session. When did we last meet? We met end of November, but then there was a sort of a winter warm in December for all the astrophotographers out there. So if you were interested in astrophotography, then that was sort of, it was all about taking the next step. And I think a number of people sort of enjoyed that, and then they've gone off and hopefully taken even better photos than the ones they were doing. So let's kick off. If I've actually got this viewed up,
probably have to select the program.
Got to select the screen. That's why it's not worked. Bingo! Right, the committee is now 8 strong. Gosh. Right, unfortunately, the men are almost being outnumbered now. This is not an Astro Society. This is not normal. Before you start, I'm just going to have a tweak on that focus there, just to get it a little sharper. But hopefully people have had to try to see the comet. If not, over the next 10 days or so, have a look for C/2022 E3 ZTF. Ziki transient fertility, I can't even say it. So that's what the ZTF is. So we've got loads of ways of getting in touch with us. We've got WhatsApp groups coming out of ears, thanks to Prim. Whenever sort of she's bored of conversation, she wants another WhatsApp group. That's great. So we've got WhatsApp groups for socials, for observing, for going to America in 2024, and the coordination team's got its own WhatsApp group as well.
And we can't see your slide.
Ah, that'll be because I'm not sharing. Thank you very much, Charles. Where's Charles hiding? Way too far. Okay, yeah, so we've got 96 members now, so we're probably going to need a bigger room. We're actually getting people, so we had quite a lot of members coming in online, and we're slowly converting them to actually looking up in the sky and actually coming in to see us. So it might be that we'll be looking for a new venue or another way of configuring the museum, or build a new museum, I don't know. But yeah, so what else we've got coming on? We've done loads of outreach in the last month. I think we've seen over 200 people in outreach events. So we've been to schools with the dome, running little shows and things like here. So I'm trying to remember, that was Wellow. That's St Julian's in Wellow. So we go observing in Wellow Village, which is about 3 odd miles away. And St Julian's is the primary school there. So we set up there and had a session up there. The Bath Abbey still loves us, and they still lock me on the tower, and unless I talk to people for an hour at end about the stars, then they don't let me down again. And this weekend we were out, just gone, admiring the light pollution in Bath. Yeah, that's absolutely spectacular, the amount of wasted light that's coming up from Bath. But we were out on Lansdowne, at the playing fields in Lansdowne, to see what we could see, and we had quite a good turnout. About 30 odd people came along to that one. So we're quite sort of keen on our outreach and sort of getting stuff done. If you haven't seen the comet, you'll find it somewhere around about here. So we've got Ursa Major, so the Great Bear. So just look between us and Draco at the moment, and you'll be able to sort of find it in a telescope, find it in binoculars, and if you've got a go-to that's internet enabled and it's had its databases updated, then you'll be spot on it every time. It's not too difficult to find, but the problem we did have is when it was down here, you had to be in the early hours of the morning to see it. Now it's getting much more into a regional sort of almost before 12 o'clock to get an okay view of it, and it's still brightening. So good luck as it gets up here. Hopefully everyone will get to see it. It's not going to be as spectacular as NEO-wise. It's not bad. It's always nice to see a comet, and the photographers have got some good definition out of the tail of it. Going forward, if you like rail strikes, there's a rail strike on the 3rd of February. So anyone who's got tickets to go to Astro Fest at Kensington, you're not going to go by rail. It's all.
When is it on the 3rd?
So it's on Friday. It's on Friday and the Saturday. Friday's the 3rd.
Not the rail strikes on the
Friday the
on
3rd.
that's it.
Yeah. So if you're going on the Saturday, you're fine. Apart from the trains will be a bit mucked up. Yeah. So fingers crossed they're not too mucked up. But it's actually a great session to go to and see loads of people. The manufacturers are there, and there used to be the opportunity to get some good deals on telescope kits. It's not so much. The last few years I've been, it's not been on actually for 3 years now. But the last time I went, there was sort of hardly any deals going. But ho hum. And hopefully you're registered for the star count in February. So inside Orion, each year the CPRE runs its star count, and you count how many stars you can see in the quadrangle. It's Beetlejuice, Bellatrix, Rigel, and Safe. And if you're in a great place, you're going to count about 35. If you're in the middle of town, you're going to count about 10, maybe less. You register and put your numbers in, and they can give a UK map of what the light pollution levels are like around you, but then they can compare it year on year and see if it's getting worse. The big news from the last one was it's getting better, but probably because of COVID. And so now COVID's it's not well behind us, it's endemic, but because COVID has passed and commerce and industry is fired up again, we're expecting it to have plummeted. In fact, the recent reports are that it's plummeted, so it's just getting worse. So the observatory up at the university is going to have to move even further away from the university to try and get.
Well, it's right with the sports lights right now.
It is, yeah. Yes, but luckily there's a good team in Claverton who are trying to fight all the new developments that are going on there, and so fingers crossed they win. Nothing against sport, but it would be much nicer if they use the right light, the right intensity, the right place, the right time, which they're not doing. Which is the irony being massive physics department, astrophysics, and lighting the scale up like I'm having a go. Because you work it there as well. No, so we've got lots of things. We've got members evening coming up in February. We've got Pete Williamson coming along. He's doing his sort of Herschel to Hawkwind talk, so that's going to be quite musical. I haven't talked to Pete for a while. If he's reasonably fit, then he might bring his guitars down and have a few riffs down. He's a bass guitarist before he retired, so that'd be kind of cool. We haven't given Ian Ridpath a topic to talk on. He's got loads. Dr. Hannah Wakeford's coming from Bristol to talk to us, and after much requests, we've got Mary McIntyre coming to visit us again in June. Thank you for the 4 people that have volunteered to have a little talkette or in February. Anyone else wants to do one? That's great. Anyway, 5 to 15 minutes, a little chat about your project or trip you've been in or what fascinates you about astronomy. And so as long as there's a space for astronomy link somewhere, anything goes. So we'll love to see you on the 22nd of February. Okay. Right. I love to speed through things because people say I talk too much. Anyway, I'm not sure if that's a record. No, not quite. I beat it by a minute previously. So I'd like to introduce David Tsang. A little more hair on the face from your promo photo, but they definitely recognised you. And talking about extreme stars and effectively neutron stars and all his research and work that's been going on. I actually met David, first of all, while asking a question after about 3 pints at a Pint of Science event, gosh, maybe 5 years ago, after being absolutely fascinated about the surface of neutron stars, because I just assumed they were just this amorphous blob, sort of sphere made of neutrons, and my mind was blown away. It could have been the beer, it could have been the talk, but I think it probably was the talk. David's done gosh, how many you've been sort of based in the States as a research fellow for?
For a decade, and then
you've come over to Bath.
Yeah,
and it's lovely to have you. You've been here for quite a while now.
4 years.
4 years. Oh, it's local now.
It's very nice to meet you all. We're up at the university. I think you had Patricia
We did, yes.
I guess a couple months ago.
November, end
Yeah.
of November. She said she was going to give you all the hints and tips
Yes.
about how bad a crowd we were.
She said your general meeting was very interesting. So I'm a theorist, which means that you guys all know much more about telescopes than I do. I live in fear that they'll lock me in an observatory by accident and I'll crash the telescope into a wall. But so far that hasn't happened and I'm still employed. So I'm going to tell you about the afterlives of stars, more specifically about a particular kind of star, a neutron star, which is the topic I study the most. And I've called this Astra and Extremis to imply something about how extreme these objects are. Also, Latin for stars in the end. This is one of the end states of stellar evolution that can occur. So, there we go. The sort of life cycle of stars in the universe is a little bit complicated, but like any sort of life cycle, from a star-forming nebula of gas, a protostar will form. And if the star is about the size of our sun, it will form into a red giant, launch winds in a planetary nebula, and eventually become a white dwarf. So that's the end state of, that's the fate of our sun, it's going to become a white dwarf. The winds from that planetary nebula will feed into star-forming nebula, and the cycle continues. If it's a massive star, about somewhere between 8 to 10 times the size of the sun or more, the star will form a red supergiant fairly quickly, actually. The good rule of thumb is the larger the star is, the faster it burns out. So these young, very blue stars will become red supergiants after a few million years, and then supernovae. And depending on their initial mass and their metallicity, the amount of heavier elements that are in them, they can become either a neutron star or a black hole. And the stuff that comes out of a supernovae, and also, as we'll see later, the stuff from neutron star mergers, feeds back into star-forming nebulae, and the cycle continues and it generates a whole new generation of stars, this time seeded with the ashes that are left over from the stars that came before it. So, here is a nice little animation of a supernova going off. And the leftover in the middle there is well, in this animation is a neutron star, and this is what I want to tell you about tonight. Neutron stars are dead stars. They're stars that have passed. The supernova has gone off. They're no longer burning their hydrogen fuel, but they're not completely dead. Well, actually, you can think of black holes kind of like ghost stars, right? Their physical matter has sort of passed beyond the veil, past the horizon that can sort of interact with the rest of the universe. All that's left is their gravity. Neutron stars are the closest you can get to a black hole without becoming a black hole. White dwarfs, in comparison, are sort of much larger objects, even though they're still quite dense. So, we don't go quite, our solar system won't become quite as extreme. But of course, Earth won't really make it past this stage. So, we don't have to worry about it. The most well-known example of a neutron star, or of a supernova causing a neutron star, is probably the Crab Nebula. I'm sure many of you have seen this before. But the Crab was a result of a supernova. We know exactly when it happened because it was recorded in 1054 AD by Chinese astronomers. And at the center of the Crab Nebula is a compact object that emits pulses at 60 times per second. And that is the Crab Pulsar. Here is a movie, hopefully, of, I think this is X-ray and this is infrared, of the Pulsar Wind Nebula. That's the wind of this pulsar pushing out against the gas and sort of causing these ripples of emission. So in the very center of this, of the Crab Nebula, is this object. You know, you of course recognize Orion. Up here is Beetlejuice. Beetlejuice will of course become a neutron star very likely. In fact, you know, we're all very excited that it could go any day now. And by any day astronomically, of course, I mean any millennia now. It's going to go supernovae and leave behind a neutron star. It's, you know, we're overdue for a supernova in the galaxy. Usually they're once every couple of centuries, maybe every 1.5 centuries or so for a normal galaxy. We've been several hundred years now without a supernova. So, you know, Beetlejuice may be the one. But actually most of the stars, all the bright ones in Orion will probably become neutron stars at some point. Neutron stars are black holes. So, you know, these massive bright stars, they, you know, live fast, they die hard, and they become these extreme objects. So why do I care about a neutron star? I'm a physicist, and you know, I am an astrophysicist by training, but I care about neutron stars because the cosmos provides the only laboratory where sufficiently extreme conditions are achieved to test new ideas about particle physics and other fundamental physics. So by studying things like neutron stars, we are in effect learning something about fundamental physics. And this is the sort of sentiment that drives me. By understanding what's going on within a neutron star, we can figure out new ways to test physics, to learn something about the fundamental forces that sort of that make up the universe. And because neutron stars are the most extreme objects in the universe, we can learn some of the most learn about the details of physics that we can't get to otherwise. Neutron stars were first discovered by Jocelyn Bell Burnell, famously snubbed for a Nobel Prize. Something to do with, oh, I don't know, her gender. But as a graduate student, she discovered pulsations coming from what turned out to be Pulsar CP in 1919. I think this was like November 1967. At first they were labeled little green men. Nobody knew what they were. And it turns out that these were radio signals coming from a spinning neutron star. Okay? And this launched the age of pulsar astronomy. A radiation beam comes out of sort of the magnetic axis of a neutron star, launching radio waves and other emission. And these neutron stars are spinning so that there's this lighthouse effect. So if you observe the radio sky, you'll see these pulsing objects. Now, I doubt many of you done any radio astronomy before. You could do it with like an old satellite dish. This is an experiment that, you know, undergrads would put together on the roofs of physics buildings sort of the world over. You could even do it with like the observatory that Jocelyn Bell Burnell observed this at was just basically a bunch of wire hung out. But these spinning neutron stars basically sweep across, and when the beam sweeps into our line of sight, you get a pulse. And that's why we call these guys pulsars, pulsing stars. Here's you know, anybody recognize this image? Yeah, so of course this is the Joy Division, Unknown Pleasures album, right? This is taken from, they just decided to look cool. And this is taken from a thesis of someone who graduated from the same graduate school that I did. Of course, you know, the year I was born, but still. This was a plot from somebody studying pulsars using the, I think, was it Arecibo? It might have been Arecibo, which is the big giant dish that was in GoldenEye. That's actually since very recently, sadly, suffered a collapse, and they're not going to rebuild it, which is quite a loss. But there is a bigger one now that's in China that hopefully will sort of take its place. But it's very sad. I know a lot of people that work there now have to. Well, they're very excited about the Chinese one, but it's a big loss for science, for Arecibo not to be there anymore. Okay, so these neutron stars are spinning really, really fast. The Crab pulsar spins at annoyingly 60 hertz. I say annoyingly because, well, at least in North America, that's the clock rate on the electricity. So it makes it actually really annoying to detect it. It's a little bit easier here, I suppose. It's what, 50 hertz? Yeah, it's a little bit easier here. But that's really, really fast. And of course, a star like the sun or a massive star doesn't spin that fast. What's happening? Well, it's just conservation of angular momentum. From watching figure skating, which I'm sure many of you do, that a figure skater might be spinning and then she'll draw her arms in and then suddenly be spinning a lot faster. That's just conservation of angular momentum. She's reducing her moment of inertia so that to conserve angular momentum, her speed her rotational velocity has to increase. The same thing happens when that star collapses. Its radius gets smaller. All that stuff gets sort of smushed in to a smaller radius. And so to conserve angular momentum, it spins up. It has to get faster and faster and faster. The fastest pulsar that we know, I think, has a 7 millisecond. So I think it's 7 point something milliseconds, which is really, really fast for something that's the mass of the sun. So, it's a relatively extreme case of the spin up. Okay, so there's the neutron star. What goes inside a neutron star? Well, there's an outer atmosphere, which is made of hydrogen, helium, and carbon. There's an outer crust, which are basically ions, electrons. It's a lattice of ions with some electrons inside. There's an inner crust where those ions start losing the nuclei. It becomes so dense that neutrons kind of drip out of the nucleons, and that those neutrons sort of form this superfluid that these nuclei sit in. In the outer core, the protons become superconducting, and you have this superfluid of neutrons and this superconducting superprotons. And then in the inner core, we don't know what happens. It's a mystery to us as astronomers. It's a mystery to nuclear physicists. We don't know, and that's very, very exciting. So to understand why doesn't a neutron star collapse into a black hole? What sort of keeps it up? To understand this, you have to understand something called the Pauli exclusion principle. Have any of you ever heard of that before? A couple of you? The Pauli exclusion principle says that two or more identical fermions, and a fermion is a type of particle. It's got to do with what's called a particle spin, but it's sort of not important. What you need to know is they're basically neutrons and electrons are fermions. And that means that they cannot coincide in the same quantum state simultaneously. So if I try to take two electrons that are the same sort of what we call spin, so their angular momentum are aligned, and I try to put them in the same location at the same energy level, it will not let you. Physics won't let that happen. So in a normal star, we have radiation pressure from the fusion fighting against the gravitational pressure, right? And a normal star is in this sort of equilibrium state where there's a balance between the gravitational pressure and the radiation pressure. As the star's fuel burns out, this balance begins to become unbalanced. This equilibrium becomes unbalanced. And that's what leads to supernovae. In a white dwarf, what the sun will eventually become, it's all burnt out, and the whole star collapses and sort of pushes everything down and down and down and down into a smaller and smaller region, into a lower and lower energy state. Until when those electrons try to sort of get shoved up against one another, they refuse to go. And what actually fights against gravitational pressure is this electron degeneracy pressure because of the Pauli exclusion principle. So it's an effect of quantum mechanics on the scale of a star that stops a white dwarf from collapsing into a black hole. Okay, and it's the degeneracy pressure of the electrons that does this. You can kind of think of the energy levels like parking spaces. So at low pressure, there's lots of space, and an electron can move around and freely sort of jump in and out of parking spaces. When the electrons sort of start filling all the energy levels, they cannot fit more than one electron into each parking space. Bosons, like photons, can. You can shove as many bosons as you want. They're like clown cars, like clowns in a clown car. They can shove as many of them. Maybe that's why they're called bosons. But anyways, you can shove them as many as you like into a small space, but fermions cannot. So electrons cannot. So what happens is you get more and more pressure building up as you fill these energy levels. Okay, because of that Pauli exclusion principle. Now, eventually, if you sort of do the calculation and you see, okay, how big is a star that's supported by this electron degeneracy pressure? What you'll find, and what the famous theoretical astrophysicist Chandrasekon found, was that eventually the electron degeneracy pressure is no longer enough to hold everything up. Okay, and there's a certain mass above which your predicted radius would go to 0. That's called the Chandrasekon mass. So basically, electron degeneracy is no longer enough to sort of fight against gravity at this point. And so what happens? Well, neutrons are also a fermion. So those electrons will capture onto protons and form a neutron. And those neutrons themselves have also a degeneracy pressure that's a lot stronger than the one for the electrons. And so the star would keep collapsing and then form an equilibrium between the gravitational pressure and the neutron pressure. Though we don't really know what's going on in here, this is sort of the general picture. Neutron stars were first proposed by Fritz Zwicky shortly after the neutron was first discovered. So he realized right away that with this particle, this neutron that's a fermion, that this kind of thing could happen, where a star could be supported by neutron degeneracy pressure. And these were just theoretical until Jocelyn Bell found them. Okay, so these stars basically collapse all the way down until they're a few tens of kilometers wide, maybe 20 kilometers wide. We're not quite sure. That's really small. That's the mass of the sun, 1.4 times the mass of the sun typically, squished all the way down into something about the size of Bath. Okay. Yeah, that's. So there's our animation again of that star basically spinning up. To give you an idea of the densities we're talking about, if you took every single person on Earth and you shoved them into a cube, that cube would be about a kilometer on each side. Okay. I mean, it would be really messy. But if you squish that cube down to neutron star densities, it would be about a teaspoon. Okay, a really, really messy teaspoon. So that's how incredibly dense this neutron star material is. I mean, literally a teaspoon weighs as much as a mountain on Earth. Okay, and that's how strong gravity is. It's sort of pulling everything down until the pressure is enough to stop it. And it requires this neutron degeneracy pressure to do that. Another fascinating thing about neutron stars is that they can have incredibly strong magnetic fields. Up to 1 million billion times the strength of the Earth's magnetic field. These can lead to, well, we already saw how those magnetic fields sort of shoot out radio waves as like a lighthouse, but they can also lead to X-rays. From the, basically these, you get particles accelerated along the magnetic field lines and sort of slamming into the top of the neutron star. It's like the aurora borealis, but you know, instead of nice lines, you have the LHC blasting you. Okay, so that causes the poles, the magnetic poles of the neutron star, to also have these X-ray hotspots. And these X-ray hotspots, basically, as the neutron star rotates, can be seen to pulsate in the X-rays. And so, with something like the NICER mission on the ISS, which is this little box on the International Space Station, which sort of stares for a very long time at particular neutron stars, we can basically see the X-ray pulsations and use timing and then some math to figure out how big these hotspots are and what the size of these neutron stars is. Okay, and determining what the size of that neutron star. Remember, the pressure that the star can sort of exert back, the neutron-rich matter can exert back, determines the size, right? Because basically it squishes down until it can support itself. So NICER's goal is to basically figure out what the relationship is between the mass of a star and the size of the star. Okay, and that tells us something about how nuclear matter will respond under pressure. And this is something we don't understand. There's many experiments that are trying to probe this, but neutron stars get to much higher densities and much lower temperatures than we can otherwise reach. So these results up here are from the NICER observations. There's just 2 pulsars, and with some very clever math, sort of working through the statistics of it, you can sort of narrow down the behavior of what's called the mass radius relationship of a neutron star. And this tells us something about how this extreme matter behaves when you squish it down. Okay. Now, I said we don't know what's going on in the core. And that's also, I said, that's very exciting. We'd like to know what happens in this most extreme case of matter in the universe. You know, the classic neutron star sort of has an inner core that is just what we call hadronic matter, just normal, regular old nucleons, the protons and neutrons, sort of tightly packed together. Okay. But it could be that the nucleons, the protons and the neutrons, break up into their quark constituents, and you get a quark gluon plasma sort of sitting in the middle there. You might have something weird going on where some of the up and down quarks transition to strange quarks, and you get strange matter inside. And you might have heard of, like, you know, science fiction things of Ice Nine sort of situations where you have strange matter infecting the cores of neutron stars and then causing other stars to collapse and things like that. But you can also have something called a kaon condensate, which is basically just a different type of particle. Instead of a 3-quark system, it's 2-quark systems. Anyways, there's lots of different theories about what's going on when matter gets this dense, and we have no idea. We have, you know, we can write down theories, but the only way is to get the only way forward is to get experimental evidence for which of these theories is correct. Now you might say, well, why don't we just test this with particle accelerators? But neutron stars sort of access a completely different part of what's called the phase space than traditional particle colliders. So you might recognize this. This is the phase diagram of water. I don't know how long it's been since you've seen this in school, but so you have, you know, solid, gas, liquid, triple point. So you have melting and vaporization, condensation, melting, and freezing. So this is a phase diagram of water that shows you, okay, at a particular pressure and temperature, what's the form of water, right? You can also write down or draw the phase diagram of nuclear matter. Here's the baryon density, that's just the number of nucleons, number of protons or neutrons, versus the temperature. So I've kind of rotated the plot there. Things like the LHC will probe sort of at about nuclear density up to higher temperature, okay? So the LHC sort of probes up here, and they might be able to get to basically what's going on in the early universe, where you have very hot nuclear density, okay? Heavy ion collisions, heavy ion colliders might be able to sort of get to up here, where you have sort of many, or a few times nuclear density, but still very, very hot. Neutron stars live in this area, where they're relatively cold to the Fermi energy. That basically means that these are degenerate objects, like the neutrons are sort of sitting at their lowest energy states, but extremely dense. So we cannot get to this state with any experiment we currently have on Earth. That's why neutron stars are such interest to nuclear physicists and other people that are interested in what's going on with these extreme nuclei. It's because we can only get to this place in this phase diagram with neutron stars. Okay. Another thing that's extreme about neutron stars is gravity. They're the most extreme gravity except apart from black holes. So we need good old Albert to tell us how to understand them. Apart from needing to know about how light bends when you study the X-ray pulsations and radio pulsations, you also need to know, well, if I have two neutron stars and they're about to collide, that causes ripples in space-time. Okay, if you have two heavy masses and you rotate them around, that causes ripples in space-time. If you took a dumbbell and spun it, you'd be causing gravitational waves, just very, very small gravitational waves, but you'd be causing gravitational waves. And so these two neutron stars, if I have two neutron stars and they start merging together, we are able to detect these mergers out to about 200 megaparsecs away from us, currently with the advanced LIGO detector. So you can also study these by finding double pulsar systems or double neutron star systems, where you have a pulsar in orbit with another neutron star, and where we are directly in the line of one of the beams of the radio pulsation, right? And so you can study the change in the orbit as this pulsation goes. And the very, very famous Hulson-Taylor Nobel Prize basically showed that gravitational radiation exists. This was the first indirect detection of gravitational waves. This was the change in the periastron due to the emission of angular momentum through gravitational waves. So, and this was the Hulse-Taylor pulsar where we had one that was a pulsar and one that wasn't emitting towards us. Okay, and this isn't a fit. This was the GR prediction. So it was a really, really nice experiment that sort of really confirmed gravitational waves. Of course, the exciting thing that's happened in the last decade is the emergence of direct detection of gravitational waves. Advanced LIGO and Virgo have really changed.
Sorry.
It's okay. Has really changed the game in astronomy. We're now sort of dealing with multi-messenger astronomy, where we get both photons and gravitational waves and maybe neutrinos, all from the same events, and where we can study these things in excruciating detail using completely different windows to the universe. So this kind of neutron star merger was first observed in 2017 with GW 170817. So two neutron stars merge. They shoot out a gamma ray burst along some axis, and then they spew out material in what's called a kilonova. That material is very, very neutron rich. And there's something called the R process, the rapid neutron capture process, where you have these nucleons, these nuclei, which are sort of way out of equilibrium because they were only in equilibrium because they were so compacted. And as they run away from each other because they get sort of flung out and they depressurize, suddenly all the neutrons would prefer to be inside them. So they all sort of stream in, and you get these crazy unstable nuclei that sort of build up, and you have this rapid radioactive decay that goes on that powers this kilonova. I'll get more into that in a second. I forgot I shifted the slide. So the gravitational wave. So here's just a small cartoon of what the gravitational waves, the gravitational wave detectors see. They see this chirp. So they see a sinusoidal signal, basically of the orbital frequency, technically twice the orbital frequency, because it's because there's two neutron stars. That sort of ramps up in intensity and frequency. So it goes whoop, so we call it a chirp. And these are extremely small, sort of less than the width of a proton changes that we measure on Earth for something that's a few hundred megaparsecs away. This would be like measuring the width of a hair from from the moon or something. I think that's what they say. But these are 4 kilometer long interferometer arms, and they measure something, the small change in those interferometer arms caused by the gravitational wave about the width, less than the width of a proton. So it's a really, really crazy impressive experiment. So you can see basically the frequency goes higher and the amplitude goes up. So it goes whoop. It's a chirp. So here is 17817. This is the frequency versus the time, and you can sort of see the color is basically the intensity of that frequency. So it's a Fourier transform, if you know what those are, in this direction and then in time. And you can sort of see this characteristic chirp signal, where you see a higher and higher frequency that goes whoop, like that. And that's the merger time. 17817 was not only the first detection of a neutron star, the masses of these things turned out to be neutron star masses, but also it was the first multi-messenger detection that we had. A few seconds, because the jet was slightly off axis, a few seconds after the merger, a GRB popped off and was detected by the Fermi Gamma Ray Observatory. A GRB is a gamma ray burst, and it was the that jet that we saw in that earlier animation. Okay, so as these things collapsed, they shoot out a jet, and that jet collides with the interstellar medium and generates a whole bunch of gamma rays that we see. And then afterwards, it becomes an afterglow as it sort of plows through more and more medium, and we see sort of X-rays and X-rays and optical and radio, all the way down across the spectrum, across the electromagnetic spectrum. We see these afterglows, and probably Patricia talked a little bit about those, right? She mostly cares about collapsars, which are stars that collapse to gamma ray bursts. These are short gamma ray bursts, as opposed to long gamma ray bursts. These come from 2 neutron stars that collide. Okay, so this was one of the ways that we knew that this was a neutron star merger. It caused a short gamma ray burst, which was theorized to be the result of a neutron star merger, plus the masses that LIGO measured, or at least the mass ranges, coincided with what we expect for a mass range for a neutron star. Okay. I'll skip that. Oh, well, I mean, you guys can, that was not intended to be in here. But these are just the light curves from what's called the kilonova. Okay, so the kilonova is that radioactive decay of emission. Radioactive decay of all the stuff that gets spewed out. As these things collide, they just naturally spray out all their interior, or a whole bunch of their interior. And that rapidly decompresses, and all these neutrons run in, and we get this cascade of our process of rapid neutron capture, which leads you to a lot of nickel 56, which is radioactive and will decay. Nickel 56 is what primarily powers the supernovae that you see. So it's the same sort of process. They're just a little bit, they're dimmer than supernovae, so we call them kilonovae. They're about 1,000 times brighter than a stellar nova. That's why they're coined that way. So here is a nice animation, I hope it works, of the R process capture. So this is the atomic number, basically the number of protons, and this is the number of nucleons. And so what happens is, this is sort of where things start from the material that gets sprayed out. And then all the neutrons sort of stream into these nuclei. And that causes this to sort of extend rapidly up the number of nucleons. That sort of gets you to really, really heavy atoms. But those atoms aren't in equilibrium. They want to radioactively decay. They don't like having so many neutrons in there. So they want to emit electrons and sort of get more protons into the mix. Basically, they want to get to these stable nuclei. These are these boxed nuclei here. Okay, so what happens is you suddenly inject, or you suddenly spray out all these atoms with a whole bunch of neutrons around. They grab those neutrons, and it runs up this way, and then decays, beta decays back down towards stability. And you generate a crazy number of really, really heavy elements. And this is in fact how we think most of the heavy elements are generated in the universe, including gold and platinum. Basically everything above rubidium, we think is generated by neutron star mergers. So all the gold in your wedding ring or in your teeth came from the merger of two zombie stars billions of years ago, which seeded sort of what Earth formed out of. Okay, a friend of mine who runs the ZTF, Mansi Kaliswal, she likes to call these bling nova because they make all the the bling. A lot of hay is made about this in the press, that these are the source of all the precious metals that we have. Okay, so we have kilonovae, we have supernovae, we have gamma ray bursts that come from these things. But I care about so I'm going to tell you a little bit about my own research now. What I care about is what do these mergers, what can we tell about the neutron stars themselves? I want to know about nuclear physics. I want to know about the sort of fundamental processes that govern what happens to these nuclei as we cram them all together. Well, one of the things that we do know is that tides can deform neutron stars. So we all know about lunar tides between the Earth and the Moon, and how they affect the ocean, right? The ocean sort of bulges out towards the Moon. If you have a neutron star that's not spinning, it just is a sphere, right? There's nothing, it's spherically symmetric. There's nothing to break that symmetry. If you have it spinning, it sort of flattens itself out, right? This is obviously exaggerated, but yeah, spinning neutron star will become slightly more oblate. But if you have a companion, like a black hole or another neutron star, in a binary with a neutron star, that will cause a tide on the neutron star. So it'll basically feel a squishing force. Okay. So how this thing squishes tells us a little bit about how it's made up, right? If you can sort of feel, if you can measure how squishable something is, that tells you about how it responds under pressure. Okay, so maybe we can use that to tell us something about how this nuclear matter behaves under squishing. But these tidal effects are really, really subtle, and they're very difficult to measure in these gravitational waves. Basically, you need a couple hundred, well, at least tens of these mergers sort of stacked together before you can sort of start to tease these out, or you wait till the next generation of gravitational wave detectors. Okay. Now, what would be nice is if we could see that these neutron stars cause, like these neutron star tides, cause some sort of other observable, something sort of, some sort of like explosion on the star. But neutron star crusts are really, really tough. They're the toughest material in the universe, unsurprisingly. It's too strong to break under this extreme tides. Even the tides that another neutron star can cause isn't enough to sort of break a neutron star just by itself. These are simulations done by a guy in Indiana named Chuck Horowitz, where he simulated for a very, very long time a very, very tiny piece of a neutron star and tried to see how much force would take to break it. And it was a ridiculous amount. Like, I forget how many times stronger than steel it is, but it turns out that something can still fracture the crust of a neutron star. There's this phenomena in physics called resonance, right? If we have a child on a swing, and I push that child on the swing with the right frequency, then that swing can get wider and wider and wider. Whereas if I just start pummeling the child at a random frequency, they're just going to fall down and start crying. They're not going to swing very high at all. The fact that you're reinforcing this motion is what's called resonance, and even a small push can result in a very, very large swing. So we can use this phenomenon of resonance if the tides sort of hit at the right frequency, the natural vibrational frequency of the star, then we can excite from very, very small tidal perturbations a very large resonance. And this is in fact what we think happens. As this orbit shrinks, remember the neutron stars orbit and get faster and faster and faster, right? The Keplers Law tells us that as you get closer and closer, the orbit has to get faster and faster, right? That means that the frequency at which the tides are pushing on the star sweep up through all the different frequencies until they merge. So as long as a resonance exists somewhere in that range, you should pass by it, and you should be able to excite a very large motion. That resonance excites a mode. That mode can get large enough that you exceed that strength of the star, and it fractures. And that fracture can lead to shattering of the crust, which shakes the magnetic field and generates dumps so much energy into the magnetic field that you blow out in a giant pair photon fireball, like electrons and positrons and photons. Okay? And these are called resonant shattering flares, and this is what I work on. We think that these things happen a few seconds before the merger, and we see evidence of this in a few percent of GRBs, of gamma ray bursts, of short gamma ray bursts. We see basically a peak a few seconds before the main flare. Okay, so we think that's what's happening. If we can get a gravitational wave signal and a resonant shattering flare, then from the frequency of the gravitational waves, at the time of that flare, we'll know exactly what the resonant frequency of that star is. Okay, that tells us, just like if Ella Fitzgerald is singing to a glass and it shatters, and if you can measure what frequency that glass shattered at, tells you something about the structure and about the material the glass is made out of, right? Exactly the same thing here. This tells us something about the nuclear physics for extremely dense neutron-rich matter. Technically, it tells us about what's going on right at the transition between the core and the crust, because of the type of mode that turns out to be excited by this. In fact, what we found out very recently was that a measurement such as this, a single measurement of a resonant shattering flare with a gravitational wave detection, would allow you to constrain a certain nuclear physics property, the nuclear symmetry energy, as well as every collider experiment that's been done. So it's really, really exciting that that we can start getting at these things with these neutron star mergers. Okay, so neutron stars are the most extreme matter in the universe. They have the strongest magnetic fields, they're the densest matter. We don't know what's going on in the core, and we'd love to know. We can study them via radio waves, X-rays, and gamma rays, mostly through pulsations, gamma rays through the short gamma ray bursts, as well as, just recently, gravitational waves. Studying neutron stars allows us to learn about fundamental physics in a way that's impossible from Earth because, well, this is the site of the most extreme things in the universe. So I think I'll just leave you with some neutron star facts. There are 1 to 2 solar masses, so about 10 kilometers in radius. Densities from 10 to the 9 to 10 to the 17 kilograms per meter cubed. Magnetic fields from 10 to the 8 to 10 to the 15 Gauss. Temperatures about 10 to the 8, 10 to the 9 Kelvin. But compared to the what's called the Fermi temperature, basically the entropy is very low, even though, like, the number on the thermometer is high. They're actually cool compared to their energy levels. They're superconducting and superfluid in their core. They're the real high TC superconductors, if you know what that means. Yeah, 716 rotations per second is the current record holder for this rotating star. And the gravity on the surface of these things is 10 to the 11 times larger than on Earth. So anyways, neutron stars are fantastic, and thank you for listening.
So that provoked a few questions. What questions have we got?
Yes.
That's a really interesting talk. Thank you so much for that. What the bits I could understand anyway. I wanted to ask, what would one look like if you actually went up to a neutron? What do you think it would look like?
Oh,
if you went up to one?
it's really interesting because a neutron star can see the back of its own head, right? Because of general relativity, because of how curved the space-time is around there. So if you're looking at a neutron star, you can see most of it from one direction. So it's weird looking. So you'd see basically this disk in the sky, and it's sort of, you'd see almost all of it
Right.
just from staring at it from one direction.
Would it, because it's not burning in the same way that the sun is.
Oh yeah, yeah.
So what would it look more planetary in its
Um,
same way, or would it look like a star?
It would be dim in the optical compared to a star, obviously. It'd be bright in X-rays, typically. It depends on the type of neutron star. A magnetar, which is one of these ones with 10 to the 15 Gauss, it's so magnetic that the magnetic field decay actually powers sort of X-rays from the surface. sort of heats the surface. So it'll be very bright in the X-rays. That's how we typically find them. So these things are I mean, we don't have pictures of them
Yeah, I take it
because
none-
they're only 10 kilometers big.
Yeah, I was going to say none
Yeah.
of them seen by visible light. I take it.
Yeah. So the best, I don't think I have there's an animation from NICER that has sort of what they reconstruct to be the hotspot. And you can kind of see that, but it's not really, it's not a picture. It's a reconstruction based on the timing of the X-ray pulsations that they see. So it's a little bit misleading to show as a picture of a neutron star. But I don't know if we'll ever be able to see one. Well, in any of our lifetimes, because it's the resolution, like, you know, to be able to resolve these things, you'd have to get a lot closer than we are to a neutron star. Yes.
There was one of your slides show that the neutron star could actually spin with the black hole, with a black hole.
Oh yes. So I don't know if I have these here. Well, okay. Yeah, so you can have a neutron star black hole merger. Absolutely.
Okay.
We think we have detected some.
So which sucks, would the black hole actually sucks in the neutron star or the other way around?
Oh, the black hole will definitely suck in the neutron star, but if the black hole is small enough, so if the black hole is fairly large, like above 10 solar masses or so, but above 8-ish, depends on the spin, the neutron star would just get swallowed whole by the black hole. So we'd only get the gravitational waves out.
Right.
That'd be the saddest case. Most likely case, actually, but the saddest case. And in fact, that's the case that we've seen. We haven't seen any electromagnetic emission from the black hole neutron star mergers. Well, what we think are black hole neutron star mergers we've detected. We have to be careful about saying that they are, because, you know, we only have the gravitational waves and there's uncertainties in the masses. If a black hole is small enough or is spinning rapidly enough, then the neutron star can get disrupted before it sort of gets swallowed whole. And that's the case where you'd sort of still see stuff spraying out. You'd get all these electromagnetic emissions. Now, what's interesting for the resonance shattering flares that I talked about at the end is that the resonance shattering flares will still happen, even for a black hole that's going to swallow that neutron star whole. So it could be that resonance shattering flares are the only emission that you get out of these things, because they happen because of this resonance before any of this swallowing or not happens. The tough part about these is it requires a really strong magnetic field, and we don't know what the population is of these. We know that there exist neutron stars that have these very strong magnetic fields, but we don't know how many of them are left after a very long time, because they it depends on if the magnetic fields thread the superconducting core, they can live for a very, very long time. But if the superconducting core sort of forms and expels the flux through Meissner effect, it's called, a certain type of superconductor will throw out flux. And if you freeze that superconductor too slowly, that flux gets thrown out. But if you freeze it fast enough, then sort of the flux gets frozen in. And so if the magnetic field is just sitting in the crust, you can do calculations that show that that magnetic field will decay in about less than 10 million years or so. So
what creates the magnetic field of a neutron star, and how is the magnetic axis determined? Because I would intuitively have thought it would be the same as the spin axis, but it obviously isn't.
yeah, they're actually really complicated. That's what NICER has shown, is that the NICER measurements have actually shown that the magnetic poles are actually like this.
Yeah. Okay.
So what? That's a really good question. We don't 100% know. Certainly some of it just comes from flux concentration. So the magnetic field, the star has some inherent magnetic field, right, caused by sort of solar dynamo that's going on. When that stuff collapses, when the star collapses, the flux sort of gets compressed, just like if you think of field lines, the field lines all sort of get gathered up into the star. And so that just gets more and more compressed. And so there's some of that. But probably during the supernova, there's all sorts of dynamo action going on as well. So that's how we think. These are extremely difficult simulations to run. So we don't really understand the process that's creating these things, but we know we can measure the decay of the spin of these stars caused by the strength of the magnetic field, at least the dipole component of that magnetic field. So that's how we know how strong the magnetic fields are. Yes.
So I'm fascinated by the square kilometre for those.
Yes, yes.
How might the arrival of the square kilometre?
Oh, it's going to be a game changer. Absolute game changer. We will find all the millisecond pulsars that we're probably ever going to find. Millisecond pulsars are these really old pulsars that probably stopped. So I don't have a PP dot diagram to show you, but if you plot the period versus the derivative of the period, that how quickly the period is changing for each of the pulsars, what you'll see is there's this line that you don't see anything past. And that's called the death line. Once these things sort of spin down past a certain point, you don't view them, you can't see them anymore. Basically, they stop pulsating, they stop emitting the radio waves. We don't know why. It's got something to do with this pulsar mechanism that what we don't actually understand what causes the radio emission to begin with. We have vague ideas, but nothing too solid. But we know that it turns off after a certain point just from observations. A millisecond pulsar is a pulsar that's that's been in binary with a different star, and that star has donated its gas, and that gas has spun that pulsar back up again, and it's spun it up really, really fast. And so it starts emitting once more, but with a much weaker magnetic field because the field lines have gotten buried by the stuff that's fallen onto the star. That sort of is twofold. It makes it easier to see because it's sort of wider angle. But anyhow, those things are fantastic for us to be able to see very, very low frequency gravitational waves. You can build what's called a pulsar timing array to look at the variations in the pulsations of these stars, because these millisecond pulsars are timed exquisitely. They're the best clocks in the universe. And so if you can sort of see the arrival times of these pulses and see how that varies in the sky, you can use that array to be like a big gravitational wave detector for gravitational waves of the nanohertz. So the more of those you have, the better that is. And the SKA will revolutionize that. I mean, it's just basically going to tell us everything that's going on in the radio. The hard part of the SKA, of course, is just the sheer data volume. It's going to be the biggest data challenge on the planet. So a lot of it's based up in Manchester. That's where sort of the SKAO global headquarters are, up at up at Jodrell. So yeah, it's an exciting time, and really looking forward to the SKA coming online. Radio pulsar observations they are not the current hotness. I feel like people have been chasing the kilonova and gamma ray burst emissions from these things because of the gravitational waves, because this very exciting chase. 17817, basically all the telescopes on Earth were looking for the kilonova. It was an absolutely crazy time, and everybody was racing to be the first to find it. I feel like Once the SKA comes on, I feel like, you know, the people that have been studying neutron stars all this time, which are the pulsar astronomers, will sort of get back into the forefront.
At inner core, are there any testable hypotheses about sort of which of the different models might be right?
Yeah, so the core turns out, the mass and the radius relationship turns out to be more or less sensitive to what's going on in the core. So by constraining that, we can constrain what kinds of cores there can be. Now, it's a bit difficult because we don't know, we know so little about the constraints in that really, really dense matter. You can kind of construct models that will work whatever the observations are. So you need other ways of probing these things to distinguish the different, like, you know, strange star models versus kaon models, or versus just purely hadronic models. One of the ways that we're thinking about doing this is using, if we can get a measurement of the resonant shattering flare at the same time as the tidal components of the gravitational wave, which is a difficult measurement. Those tidal measurements from the gravitational wave, basically how much response to squishing, that is also sensitive to the same stuff as the mass radius. It's sensitive to mostly the core stuff. So if you can get those simultaneously, the resonant shattering flare and how squishy it is, then that tells you if maybe the core is sort of consistent with the properties, the hadronic properties that we're measuring, sort of at the core crust transition, which is where the resonant shattering flare occurs. And that sort of simultaneously may tell you, okay, you can't have purely hadronic, or purely hadronic is okay. So that you need to be able to look at multiple depths in order to be able to distinguish those. And there's very few ways of doing that currently.
Sounds like there's a few more PhDs left in it.
Oh, yes, yes, yes. I mean, it's such an exciting time because, you know, gravitational waves lets you really look deep into the core of these things. You know, even nicer is basically only studying surface emissions, right? Whereas the gravitational waves, it's the matter that's doing this. You can see right through everything. It is really a completely new way of looking at the universe. So it's a very, very exciting time.
Simon, can I have one?
I'd like to thank David for coming along for the talk.
Simon, can I ask a question?
Round of applause. Thank you.
Simon, can I ask a
Thank you very much.
question?
And I hope to see everyone sort of at the events and things we've got planned, and sort of observing going on. And if we can't see you before, we'll see you at the members' evening. Now, Prim, you're dragging us to the pub. Anyone that's interested in going along to the pub, then Prim's your person. We had about 8 wandering along last time. But if you've got any questions, hang back, you can ask me a question. If you're going to lose some more bits of your telescope, then I'll find them for you. Whatever's going to happen. We talk about sharing, observing, coming to meeting, observing meeting nights. Hopefully you discovered sort of one of the benefits of actually going to a members observing night, where people just help each other. They sort of say, oh, okay, I'm having trouble aligning. Well, try this, try that. And if it does turn out that your telescope is based in Alaska, then we'll correct it. We'll get it based in but it's those hidden problems. And once you know about them, you go, oh, yeah, I know about it. I'm never going to do that again. That's great. Or bits falling off your telescope, that's fine. Or people mistaking stars for planets, that kind of stuff. But also, as Prim says, I also make mistakes as well. So there's a little bit of a quiz there. How many mistakes does Simon make on an observing evening? It's usually at least 1, but quite often 2 or 3. But I hope to see you soon. Thanks very much for coming along. Thanks, everyone.